Hello and welcome to Chapter 22 of Lec 50B. So today we're going to look at alternating current in the capacitor, specifically with capacitive reactance. Alright, so we've already learned about capacitance and inductive individually and how they behave in DC. And now let's look at how they react to AC. Now because a sinusoidal AC voltage changes continuously, there's some RMS capacitor current at all times. Now the ratio of capacitor voltage to current, remember voltage equals the current times the resistance, or the resistance equals E divided by I. That's still true, even if our R now is going to be our capacitive reactance. So let's say we have a circuit like here where we have a sine wave and then just a capacitor. So we're now in this circuit, we're going to have our voltage, our capacitance, and then we'll have a flow of current, right? So Ohm's law is still true. So E is still going to equal I times R, but instead of R, we're going to have our capacitive reactance. Okay, so that Ohm's law is still true. So keep that in mind when we go through this. So for DC, the capacitor is an open circuit. So this allows it to block direct current and to pass an alternating current. So when our circuit has DC on it, that gets blocked, right? So it's going to block DC but allow AC. So the same is true in an inductor. The current is always changing in sinusoidal. So the voltage is changing in the capacitor and the current is changing in an inductor. So there's some effective opposition to the current drawn by a coil at a given frequency. This is called the inductive reactance. This is determined by both inductance and reactance. Okay, so when we look at this, and now we're only going to look at the capacitance this week, and we'll look at the inductance reactive next week. But here's some background information on that. Now, inductors tend to block AC and pass DC. So when we talk about this stuff, just keep in mind that whatever an inductor does, the capacitor kind of does the opposite. So a capacitor passes AC, blocks DC, and inductor passes DC and blocks AC. All right? So let's keep going here. Now there's a formula here where the quality factor, or Q, is expressed in terms of inductive reactance as a figure of merit to show how inductive a coil is compared to its internal resistance. All right? Now, another thing, so now let's look at this AC. So here's a simple AC voltage source with a capacitor, and it shows the voltage is the red line here, right? This is voltage, and the current is the green line. So notice the voltage is 90 degrees behind the current. So the current starts here, and then 90 degrees later the voltage starts. So the phase relationship in a purely capacitive, the voltage is lagging behind the current. All right? So at the beginning of the first quarter cycle, the current has just passed through zero and is increasing in the positive direction. Since the 0 point is the steepest part of the sine wave, the current is changing at its greatest rate. In other words, the greatest number of electrons are moving off of one plate and onto the other plate. The capacitor current rises to its maximum value at the 90 degrees point. The voltage at the 90 degree point crosses 0 and proceeds towards its maximum. 90 degrees later, the voltage across the capacitor is maximum. The capacitor is fully charged and there is no further movement of electrons from plate to plate. So the current is 0 at that point. All right? So at the beginning of the first quarter cycle, so when the capacitor voltage is increasing, the current is decreasing. And you can see that on that curve. So as the voltage increases, the current decreases. So when this is maximum, this is at 0. And when this is at maximum, this is at 0.
Thank you, we work.
All right? So we want to keep that in mind as we go through this. Now, when the capacitor voltage is increasing, the current is decreasing. After the capacitor reaches its maximum, it starts to decrease. All right? So at the voltage of 180 degrees, the voltage has dropped to 0. This means the electrons are evenly distributed between the two plates, and the current is at its maximum negative value. So here we are when the voltage is at 180 degrees, the current is at its maximum. So here's the voltage here at 180, and the current is at its maximum negative value. All right, so that's just some basics about this. Now, another way to see the 90-degree phase shift is to examine the capacitor charging equation, where I current equals the change in the delta V over delta T. Note that at the first instant in time, T0, the denominator is 0, thus I see as maximum. Also at this time, each plate has the same number of electrons, and the capacitor acts like a short, and the potential difference is 0. Now if the current is maximum and voltage is 0, there's a 90-degree phase shift. Because the plates of the capacitor are changing, the capacitor seems to pass the alternating current. Actually, electrons do not pass through the dielectric, but they're rushing back and forth from plate to plate, constitute a current flow in the current. So here's an example on your meters, right, our oscilloscopes. When we change it from DC coupling to AC, it basically, this capacitor here blocks any DC. So on your scope, you'll see that move up, right? So it won't move from the DC, it goes down to, there is no more DC showing when we change that or switch it to coupling. And that's what that's doing there. All right, so now the capacitive reactance. So capacitor is often in opposition to current flow. This opposing opposition arises from the number of electrons that go back and forth. And current flows very easily when the capacitor is near its discharge state, as there is very little opposition from the series opposing voltage across the capacitor during this time. So you can see that as the frequency increases, will decrease the opposition offered by a capacitor. So the capacitor remains near its discharge state due to the increased frequency. The opposition which a capacitor offers to AC is inversely proportional to both the frequency and the capacitance. And that is called capacitive reactance, or X of C, right? So in this week's homework, you're going to solve for X of C several times. All right? Now, the formula here is X of C, which is measured in ohms, equals 1 over 2 pi times the frequency times the capacitance in farads. Okay? So if we have a 10 microfarad capacitor and a frequency of 1 kilohertz, the X of C is going to equal 1 over 2 pi times the frequency times the capacitance. So 1 over 2 pi times 110 the frequency is 1 kilohertz times 10 to the negative 6 farads, you get 15.9 ohms. All right? So this formula is going to be the main one you're going to need to know to find capacitive reactance in a purely capacitive circuit, so only a circuit with a capacitor. Later on, we're going to see it in next week, in the second part of this chapter, the X of L, which is the inductive reactance. And then after that, we're going to look at how they work together with resistance, right? But for now, we're on a strictly capacitive circuit. So determine the capacitance reactance of a 0.001 microfarad capacitor when the frequency is 4 kilohertz. So on that one, you just say 1 over 2 pi, then the frequency is 4 kilohertz times 0.001 times 10 to the negative 6 farads, and you end up with 39.8 kiloohms. Now, you may have to solve for C. So notice it's X of C equals 1 over 2 pi F of C. If you multiply both sides by C and then divide both sides by X of C, you in essence just move or replace the C equals 1 over 2 pi F times the X of C. So what C is needed for an X of C of 12 kiloohms at a frequency of 10 kilohertz. So on that one, you just say C equals 1 over 2 pi F of X of C. So 1 over 2 pi times 100 kilohertz times 12 kiloohms, and you end up with 132.6 picofarads. All right? Now, you can also find the frequency at which the capacitor has, again, if we go back to our original formula here, we know X of C equals 1. So again, if we multiply both sides times the frequency and then divide by X of C, we end up with just moving the frequency equals 1 over 2 pi the capacitance times the capacitive reactance. So in this case, what frequency does a 0.01 microfarad have an X of C, or capacitive reactance, of 800 ohms? So you just take 1 divided by 2 pi times 0.01 times 10 to the negative 6 times 800 ohms, and that's 19.9 kilohertz. All right? And you can also figure out how much current flows in the circuit in the example above if the source is 120 volts AC. So in this one, we know X of C equals 800. The voltage is 120 volts AC. So we know our Ohm's law is E equals IR, or E equals IX of C in a purely capacitive. So now we want to solve for current. So I is going to equal E over X of C, which is going to equal 120 volts divided by 800 ohms, and that will equal our solution here, which, let me go back here, which is 150 milliamps. All right? So that's all I want to cover this week. There's a lot in this, and I really want you to practice. Go through all the examples in the textbook, and just draw some circuits and solve for X of C, solve for F, solve for capacitance C, and then once you get the X of C, look at what the current would be, what the voltage would be at a certain current, and start getting comfortable working with those formulas. All right. So then the last step here is, because capacitive reactance is an opposition expressed in ohms, the series or parallel reactances are combined the same way as resistance. So in a series formula or circuit, X of C total equals X of C1 plus X of C2 plus all of them. So it's just like RT equals R1 plus R2 plus R3 in a series circuit. It's the same with the capacitive reactance. And then parallel is the same. It's 1 over the reciprocal. Now this is opposite of the capacitance. The capacitance, remember last week we saw in a series circuit, the total capacitance equals 1 over C1 plus 1 over C2 and so forth. And then in the parallel, capacitance is C1 plus C2 plus C3. So don't get this mixed up, because the capacitive reactance is the same as resistance, whereas the capacitance is the opposite. So series is calculated 1 over the C1 plus C2 plus C3 and so forth. All right? So that's it for this week. And I've graded your midterm, or your test 1, and most of you did really well. So good job on that. And we will see you next time on the next video.